So now what we'll do is we try and get some quantitative description in place to describe the fluorescence process, so we can estimate signals that we might get when we excite molecules in a microscopic samples through the microscope and exploit this fluorescence process. So it is clear all molecules, all dye molecules, when they are at room temperature, are in their ground electronic state, because the thermal energy required to get them into the excited state is far too high. You need millions of degrees to get significant populations in excited electronic states. So what this means in practice is that the problem of fluorescence always starts first in the ground state, and you need to supply energy, usually in the form of photons, to get the molecules in the excited state, and then from there they start trickling down at a rate A and M to give you the fluorescent signal. And we want to describe this. So we need to know how many photons are absorbed first, how many molecules are in the excited state, and then how quickly do they come back down, and what are the processes that diminish the fluorescence because of quenching. So let's begin by looking at the absorption part first. So for the number of transitions when we supply excitation light. And to do that, we look at the Beer-Lambert law. And so to consider this, think of a little cuvette. Looks like this perhaps. And it is filled with a solution containing a dye. And we have a light intensity or irradiance coming in at an initial intensity I0, and it passes through the dye solution, or whatever the sample solution, and it comes out at intensity I. Okay, so in between, some of the photons in the light beam here are absorbed by the solution, and so of course the intensity will be diminished by the number of photons that have been absorbed and have excited molecules inside the solution. So if I were to plot on a graph, so let's just plot this like this. So we start at the entrance of the cuvette, and then we have an axis like that, and then the exit of the cuvette is here. And so if the cuvette length is L and that is X, then the initial intensity that comes in, so it comes in here at intensity I0, right? And then you have absorption, so the light decreases, and then it comes out, and it comes out at an intensity I. At position L, after absorbing through a length L of analyte. And Beer-Lambert's law is that the intensity coming out is given by the intensity going in times 10 to the minus epsilon capital C capital L, where L is the length and epsilon is in units of per mole, cubic decimeter per centimeter, and it is called the molar extinction coefficient. And L is the length of the cuvette. It is in centimeter. Note the units are a little funny. So this is per centimeter of absorption length, and this is centimeters, the length over which you absorb. And the reason why it's centimeters is because in standard spectrometers, absorption spectrometers that you can buy, you get cuvettes that are exactly 1 centimeter long. So you know that the absorption takes place over a path length of 1 centimeter. So very often this L will just be 1 centimeter, and that's the reason for that. And cubic decimeter, that is essentially because the absorption is calculated for a concentration of C mole per cubic decimeter. So the units all make sense; they cancel out, and so all this works. So this is the concentration, the molar concentration. So it's moles per liter. And note, I deliberately wrote this as capital C, so just so you don't get confused with the lowercase c, which denotes the speed of light. So they have nothing to do with each other. Okay, the transmission T is given by I over I naught. So it's essentially the ratio of what comes out over what went in. That's called the transmission, and that is just I over I naught is just 10 to the minus epsilon capital C L, and that's called the transmittance. And we can now write A is given by, not to be confused with Einstein coefficients, this A is something different. It's not A N M or anything like that. We will always have subscripts for Einstein coefficients. This A is the absorbance, and it's given by minus log I over I naught. So that is equal to T. So it's minus log basis 10, and that is equal to E capital C L. And that is called the absorbance or the optical density. And so you can now tell me, so we can recast this here as I naught times 10 to the minus to the power of the absorbance. So you can tell me, you work out yourself. So if the absorbance A doubles, how does the signal, how does the ratio, the transmittance change as a result of this? How does the transmittance change as you double the absorbance? And that's a useful thing to get your head around, because it tells you also why absorption is a difficult measurement to make. Now, it's a nice measurement because, if I know what comes out, if I knew what went in, if I know what the length was, and if I know what the extinction coefficient was, then I can work out what the concentration was. And it's totally quantitative, this thing. You need to know nothing else. You can very accurately determine concentrations using this technique, but just this ratiometric measurement. But there is a big problem, and the big problem is that you're comparing a bright signal. If there's nothing in there, then I is equal to I naught. So what goes in comes out if there's no absorption. So it's exactly the same intensity. Now, what is the minimum amount you can actually detect? So if I over I naught is 99%, only 1% is absorbed. Detecting a change in intensity of 1% on a bright signal is really hard. I mean, if I turned the lights here down by 1%, I bet you wouldn't see it. You wouldn't see any perceptive change in my brightness on this picture here. It's very, very hard to do that. So this is the problem with absorption. It's not it's a nice measurement technique, but it is not a zero background technique. You're actually looking at a constant background signal and then slight decreases from something that is initially bright. When there's no signal, you have lots of bright stuff coming through, and then you diminish it by having absorption present. On the other hand, if because of this exponential behavior here, if you have a very large concentration, then of course what will come out very quickly goes down to zero, right? So because of this exponential decrease, and then you get no light coming back through, and then you can't measure anything either. Then you cannot determine I over I naught very well. The transmittance can't be looked at. And what that means, that in practice, absorption on its own is a measurement that is only possible for 2 orders of magnitude at most of measuring concentrations. So you need to have A between 5% and maybe between 5% and 100% for you to say anything. So before, if you have much less absorption, you can't see it, and if you have if you have no less absorption than 5%, then you can't detect it, and if the absorption is too large, then of course you get no light coming through at all anymore. But let's now look at the other effect. Let's look at fluorescence again. So of course we do first absorb in the sample, but then the sample emits light. So the absorbed photons from the excitation are now emitted as spontaneous emission. And now I'm focused on detecting those instead of looking at the transmitted beam. So what does that signal give me? So if I look at the fluorescence quantification, we have F is equal to K P naught times 1 minus 10 to the minus A times theta F. Now, the fluorescence signal F is in watts given by the power incident on the sample. This is the excitation power, P naught, and times the fraction of light that's being absorbed. That's just given by Beer-Lambert's law. So 10 to the minus A is what's absorbed. So this is the difference between what went in and then what came out. And so, of course, those photons that don't come through have been absorbed. So that's the number, the fractional power that has been absorbed. So fraction of P naught absorbed by the sample. And K are just some instrument factors. So this is some proportionality constant. It depends on how good your detectors are, what the conversion rate is from optical signal to electronic signal, and so on. And how you collect the photons. You remember the fluorescence photons go in all directions. So how many of those are you collecting? And then finally, there's this very important factor, theta F. And theta F is called the fluorescence quantum yield. So it's given by ANM over ANM plus Q. I put subscripts in there, so because just to make this explicit that we are only dealing with a 2-level system here. And so this is called the fluorescence quantum yield. Essentially, it tells you if I put molecules into an excited state, what is the likelihood of them emitting fluorescence? So it's the rate at which fluorescence takes place over the total loss rate, which is fluorescence plus any loss processes such as quenching. And so for very good fluorophores, that fluorescence quantum yield will be close to 1, i.e. that Q is 0, so you get A over A, which is ANM over ANM, which is just 1. And for inefficient fluorophores, Q will dominate, and it could be a factor of 1,000 lower, as we've seen previously. So designing dyes and designing system where theta F is very high, and which you can get even in solvents and environment by protecting the dyes and so on, is the key to get good signal. As a question to you, I would like you to think how the fluorescence quantum yield is related to the fluorescence lifetime that we discussed in the last lecture. So what does it mean? What does it mean for the fluorescence quantum yield if the lifetime is short, for example? Think about that. And when we get to the lifetime lecture, you can see how this might become important. Why and how we can actually measure what the efficiency of a fluorophore is using that method. So for dilute samples, i.e. samples for which the absorbance is really small, let's suppose that for samples where A is much less than 0.05, less than 5%. So less than 5% of the sample is excited. In practice, when we deal with biological fluorophores in a microscope, for example, this is always the case. We have very small numbers of most of the photons in the excitation beam are not used, right? So to excite, because the density of fluorophores is low. In that case, this fractional absorbance is just 10 to the, is just given by 1 times e to the minus 2.3a. So this is just turning this into a natural exponential here, so 10 to the minus a is equal to e to the minus 2.3a, and so you can do a series expansion of this, and then that becomes, for small a, that becomes just 2.3a, okay? And that is a good approximation for most fluorescence situations that we encounter. Now, if I put this into this equation here, then what we end up with is F is equal to 2.3 times K P naught theta F, fluorescence quantum yield, times A. And that is equal to 2.3 Kp naught theta F times epsilon big C concentration times L. So that these are, of course, this is just the absorbance A. Okay? Again, just to repeat, don't confuse that A with these A's here. These are Einstein coefficients, this is the absorbance. All right, so this is what fluorescence is. This is the fluorescence signal, and it has several really neat features. So first of all, the fluorescence signal is linear with C. So it's linear in concentration C. Now that is different to absorption, right? Where you have an exponential dependence on C. So that is a really nice feature, so that if you increase C by a factor of 2, so that in this regime where you have low amounts of absorption, which always holds really, you have a linear increase in the intensity. The point is that this linearity holds over many orders of magnitude. You can, depending on the detectors you use, you can detect between 1 photon and tens of thousands of photons on the same detector. So the concentration, so you can actually adjust the concentrations over that range. And as we've seen in absorption alone, this wouldn't be possible because the concentration can only be varied by a factor of about maybe over 2 orders of magnitude. That's the maximum for us to be able to see this. And the other thing is that the limit of detection, or LOD, is on a 0 background. So the limit of detection for fluorescence is single molecules are possible. Quite routinely, if you come to our laboratories downstairs, we do this every day. We are able to pick up single photons, and this is now not even a big deal anymore because the technology has moved on so much that the camera sensitivities are enormous. The quantum yields of the camera systems are very high because they also have to convert, of course, a photon to an electron with very high efficiency, right? And they can do this now with very high quantum efficiencies. So so detecting single molecules is very much possible nowadays. So it's much lower than what you would get with absorption. So it is also linear with power. So in this regime where the absorption is small, the fractional absorption is small. It is linear with the amount of light I supply, so I can get more signal by turning up the power. And because we looking at Stokes shifted light, we can very easily discriminate contamination signal from the excitation light. So although P naught may be large compared to the power in the fluorescence signal, it is still easy to discriminate against it simply by filtering out the color of the excitation light. And these are important points to remember in this course. Okay, in the last part of this lecture, what we want to do is we want to look at the rates of transitions in more detail. How quickly do we pump population up? How quickly does it come back down again? What is the equilibrium between the different rates? What is the relative importance of spontaneous emission, quenching, stimulated emission up, stimulated emission coming down? And to do that, we actually need to solve a simple differential equation system to look at these rates. I mean, all the Einstein coefficients are rates, so it's very easy to set up this equation system. So let's do this in this last part because it's important then when we come to the application parts of our lecture course. Transition rates. Right. So if you look at this figure again, we consider a two-level system, and just to make that very explicit, I've written for the lower level rather than level M, I just call it level 1, and for the excited state level that we called N before, we just call it level 2. So it's a two-level system. And now the rate at which fluorescence goes up is B12, it's little b12, so b12 will be just b12, so it's big B12 times U of nu, so that incorporates this rate. And so this is stimulated up, this is the rate of stimulated emission down, this is the rate of spontaneous emission, this is quenching. There could be, the model that we consider, it's these four processes are all we calculate or take into consideration, but you could easily put in a loss term. For example, it may be that some of the molecules may dissociate when they're in the excited state, or there may be another event that actually that takes that excited state away. So other mechanisms so essentially the excited state population is lost, but not by returning back to the ground state, but by forming other complexes, for example. So the molecule is just gone, essentially, in that case. That is not important for what we will do in this course, but I put it in case that you may want to consider these rate equations also for that possibility, right, in a research application. But for now, let's just look at this process as it is. Let's say we have population can be driven up at rate B12, can be driven down at rate B21, and of course these happen exactly at the same frequency. So when the laser is shining onto this, it really depends on whether there's more population down here or more population up here, whether that one dominates or that one dominates, right? There's also spontaneous emission, and there's quenching. And so the rate B12 is equal to B12 times U of nu, and that is equal to B12 times I nu over C, right? So this is for power flux for lasers, and this is for the spectral radiation density. And of course the same thing holds also for B21. Just swap these subscripts. So B21 is equal to B21 times I nu over C. So all these rates here are in units of per second. So this c, just to be sure, is the speed of light. So let's look at the change of population in this lower level. I said before we put any light on this system, everything is down in this ground state. Because these electronic energy levels are really spaced over a big distance, you can assume that all the population is in that lower state before you start. But now you put light on at this intensity I nu or at this spectral radiation density U nu. Then the rate of change of population in the lower level is dN1 by dt is equal to minus N1 B12 plus N2 B21 plus A21 plus Q21. In other words, it loses population at this rate. So it loses population at that rate going up, and it gains population from whatever comes down. So from in the upper state. And you can write a symmetric equation for the population in the upper state, and that is given by N1B12. So what this level loses, this one gains, obviously, so it's completely symmetric. And what the top one loses appears as negative here. So it's B21 plus A21 plus Q21. And as I said, I've ignored that loss term. So I just ignore it, right? So otherwise there would be an extra loss term in this equation here. So we ignore it. And so in steady state, actually, this system is closed, right? So anything that leaves from down here will end up here, and anything that leaves from up here will come up down there, because we just ignored this other loss mechanism, right? So what this means, therefore, is that dN1 over dt plus dN2 over dt is equal to 0 at any one time. That must be the case. So in other words, N1 plus N2 is equal to N1 naught. And so N1 naught is the population. So this here is the population, total population. So it's a total number of molecules. But that's the population in the lower level prior to exciting, prior to putting light on it, because we said everything will be down in that ground state, nothing will be up in the upper state. All the molecules will be down there at t equals 0. Okay, so at t equals 0 we switch the light on, and then we cycle this population around. Okay, so you can integrate now. Let's just look at this equation then. In steady state, let's integrate this equation. First of all, so if you integrate this equation, then you can get N2, I'll leave that as an exercise for you, just substitute this in, N2 of t is equal to B12 N1 naught over R times 1 minus e to the minus RT, okay? And so what we've done is we have written R is equal to B12 plus B21 plus A21 plus Q21. So essentially, R are all the rates in the system. So it's the rate up, rate down, rate down, rate down. So it's the sum of all rates that take place in the system. So the quicker these rates, the more quickly this thing here will decay. So let's have a look. Sorry, the more quickly actually the population will build up. Let me just explore this with you. Let's just look at this equation here. So what you can see is that if t is very small, at t equals 0, that term is 1. So you get 1 minus 1, so the initial population in N2 is 0, obviously, right? Then t increases. This term is now becoming less than 1, and so you get a positive. This term will turn positive, and so the population will rise in time, and then at t equals infinity, essentially. This term here will become 0, and you will reach a steady state population of B12 N1 naught over R. Okay, and so that steady state population is given by N2 steady state is equal to B12. Let's just write it this way. N2 at t equals infinity is equal to B12 N1 naught over R. Okay, so that's the steady state solution for this. If I go back to this equation here, let's look at very small t. Then just as we've done for the Beer-Lambert law, I can expand this term here, and I get a term that will be proportional to RT for this part down here. And so so that means that initially, so we get RT here, so we get B12 N1 naught over R times RT, so the R's will cancel, and I just end up for small times, so for R times T much less than 1, the population in N2 rises linearly, and we get N2 T much less than 1 is equal to B12 N1 naught times T. Just builds up linearly. And then it sort of rolls over, and it rolls over and reaches that steady state value here. So what this means is that you get a signal that starts rising, and then it reaches steady state, and that is given by, so that's N2 of T, and that's T, and the steady state solution here is given by B12 N1 naught over R. Okay, now very interestingly, if R is very large, then this drops down, right? For the same B, so you get a lower level, and the reason for that is that you get more loss terms here, right? For the same B's. So then these two terms dominate in this R, and therefore your steady state population will be relatively low, right? On the other hand, if you imagine now that in R, if you have these two terms completely dominating in this particular case, we said that B12 is nearly equal to B21. We said the stimulated emission and stimulated excitation constant are similar in the last lecture. And then if these are very large, then you can ignore these spontaneous terms, fluorescence, and because essentially what will happen is you just drive up and drive down, and if these are small, they're negligible, right? So essentially driving population up, you're driving population down. So for that case, let's suppose that that B12 and is equal to B21, as we said, it's roughly the same. As we've said from the Einstein discussion, the Einstein coefficients. And if they are much larger than A21 plus Q21, so let's put it this way. If B12 plus B21 is much greater than that, and because B12 is roughly B21, then what you end up with, so if I look at the steady state value, then in that case N2 at t equals infinity will go to b12 over n1 naught divided by all this. But so this means b12 plus b21 is equal to 2b12, right? Because it's twice the equivalent roughly. So if I put that in now, if I put this into the steady state solution, I get b12 n1 naught divided by 2b12, right? Down here, we ignore these factors because they're small. So essentially what I end up is I get b12 n1 naught over b12, 2b12, which is equal to n1 naught over 2. And this is for b12 plus b21 much greater than a21 plus q21. And I just wanted to, I wanted you to think about what this result means. So if these two rates are very high, if these two rates are very, very high, i.e. this rate and that rate, and they will be high if I put a high intensity in, then essentially I drive population up, and as soon as it's up there, I'll drive it back down again with the same light, okay? And it doesn't have time, the system doesn't have time to emit photons by spontaneous emission. It doesn't have time to collide and quench down, because before any of this is likely to happen, another photon is much more likely to arrive to de-excite it down. So essentially you're just cycling population up and down. And you're doing it at such a rate. What will that actually mean? It will mean that in the high intensity case, the population in the upper state will be exactly the same as the population in the lower state. Half of it will be down there and half of it will be up there. You're just cycling it around and you're shifting it. So initially you get a linear rise, 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 rise until you reach the maximum population, which is half. Okay, and there's a very, very interesting effect now, and I would like you to think about this, but you will understand it. But there's a phenomenal consequence. And the consequence is that if you put the power up, get these two processes to dominate, the sample becomes transparent. i.e. it means when you put a photon in, a photon will come back out again in exactly the same direction. And I want you to think about why that takes place. Discuss it amongst each other and discuss it in the supervisions. And I will actually show you a demonstration of why this happens. But it must happen if you think about it. And it comes purely out from this analysis. Okay? So what we can do now, briefly, is we can actually recast these equations into a different form. We can rearrange the steady state value. So in steady state, you can recast this equation here, n2 equals b12 times n1 naught over r. You can recast that by essentially putting in the terms for b12, b21 into this equation, rearranging it. You can rewrite the steady state equation as n1 naught, now big capital B12 over B12 plus B21. We said that that factor is around a half, right? Because they're similar in size, times 1 over 1 plus I sat nu. So this is the irradiance. It's called the over I nu. So I nu is the irradiance of the input power, and I sat is called the saturation. The saturation irradiance or intensity. And what you see is that for for I knew if the laser power or the light powers, if I put a laser beam onto a sample and I would like to know how the population, the steady state population, the upper state, what it is in steady state. So after a short while, I reached steady state when I switched the light on, and the N2 population will then reach a value that is for I nu much less than I sat. And when this is very small, then it turns out that the rise in population in N2, or the level of the population in N2, is linearly proportional to the laser signal, right? And if I nu is much greater than this so-called saturation intensity, then what happens is that the population essentially reaches that level where the medium becomes transparent. Half is down, half is up, because we're just driving the system so hard that essentially whatever we drive up will drive back down again. So the saturation intensity is defined as A21 plus Q21 times c, little c as the speed of light, plus B21. Essentially, what the saturation intensity does, it's a parameter that defines, that compares the rate, the spontaneous rate, i.e. those rates that are not dependent on the laser power that I put in, with the rates that are dependent, that are driven. So it's the spontaneous rates compared to the driven rates. And so, of course, if the spontaneous rates are very high, let's go back to this figure again. If the spontaneous rates are very large, if this is very fast, you need to supply a lot of power to saturate this sample, right? And if, on the other hand, if these are very low, these rates here, it's actually very easy to drive the system into saturation with a laser, and so the corresponding saturation intensity will be much lower. I have given you most of the steps in the derivation of these things. There's a bit more algebra, but you should do this as a homework exercise and play through these concepts. It's actually by playing with this as you go along that these concepts make real sense. So we've done it now, because now we can write down what the fluorescence signal is. We get a steady state population in the upper state. And now we know that. It takes into account quenching, it takes into account stimulated driving. But now we know what the steady state population is. We know that the fluorescence signal is just proportional to N2 times the Einstein coefficient for A2, for spontaneous emission. And now, if we want to have this if the photons that come back have energy h nu, so these are per second, the number of transitions per second, so it's proportional to the number of molecules times the rate, so times the energy, so that has units of watts, joules per second is watts, and then what we need to do is, if I go back to this cuvette example, I fire the laser through, and then, of course, the fluorescence excited will now go into all directions. And somewhere I will put a lens, right? And I capture this solid angle. So this will be my microscope lens, and then I will have a detector. I just make an eye here so that you know this is the detector, so to speak. So the collection that I have will depend now on this collection solid angle. So it's alpha over 4 pi. That's the collection solid angle that I have. And then it will also be proportional to the volume that I excite. So if the laser beam has an area A, a cross section A, and I observe over a distance L in the sample, then then N2 times AL gives you so this is a concentration, it's mole per cubic decimeter, this gives you cubic decimeters or liters, and then so this together gives you the sample, the number of molecules in the sample. And you now can put in for N2 the equation you had previously in terms of the saturation intensity, and that is the number of photons you get back when I put a certain intensity I on the sample. That's what I'm collecting. And of course, this N2 here, through the rate equations, contains the quenching and the fluorescence quantum yield through the quenching, because it's and so again, the fluorescence signal will be affected by quenching pH, ion concentrations, and so on. So actually, getting absolute numbers is quite hard. It's harder than with absorption measurements. You need to know a lot about this, but on the other hand, it gives you this environmental information, which can be very useful if you understand the physics that's behind, how the environment interacts with the fluorophores. And finally, it's just the sensitivity. You can get tremendous sensitivity because photodetectors are so good, because it's a zero background signal technique. And I should just mention that this signal is in watts, as I've mentioned, as I've shown you here. Okay, so I just want to give you a very, very tiny last bit, which is shot noise. And shot noise is a quantum effect. So essentially, it comes from the fact that photons that are emitted don't come in steady streams, right? So even if you have you may have a laser beam, and the laser beam emits, I don't know, 10,000 photons per second. In fact, if you measure in a 1 second interval, maybe in some intervals it will emit 9,500, and the next one 9,652, and then maybe 11,301, and so on. And so in these intervals, the signal will fluctuate. And in fact, if you have a photon stream, so if you have a photon stream of m photons per second, then the RMS noise on that, the root mean square variation, so I just call, that's the average, if the average number of photons emitted per second, the RMS variation, the root mean square variation on this, turns out to be plus or minus square root of m photons. So in other words, if you have an average intensity that corresponds to 10,000 photons per second, the actual fluctuation, the RMS noise on that, the fluctuation is plus or minus 100 photons. So that's how the signal will vary within these bounds. And so that means that the signal to noise ratio is given by the signal. The signal is m, so that's the average number of photons, divided by the noise, and that is given by the square root of m. And that is then, therefore, the square root of m. So the signal to noise ratio for a stream of 10,000 photons per second will be 10,000 divided by 100, it's 100. So it's 100 is the signal to noise ratio. Now, if I have a stream that contains 100 photons, then the signal to noise ratio that you can get in the shot noise limit is 100 divided by square root of 100, which is 10. So it's actually significantly lower. And so the upshot of this is that if you have low signals, and you do the best possible measurement you can do in any situation, whether this is absorption or fluorescence. If you detect, let's say, M photons, then you know you're in the shot noise limit if the noise level on your signal is square root of M. Okay? If you've reached that, you've reached the shot noise limit, and that means that's the best possible measurement you can do. Okay? And so what you can do to improve this is to collect more signal, obviously. So if you integrate over for 100 times longer, then the signal to noise ratio will go up by a factor of 10 because of this shot noise. And so with fluorescence techniques and sensitive detectors and good electronics, you can get down to the quantum limit, the shot noise limit, and then you can say this then allows you to work out what the minimum concentration of something is that you might be able to detect, and for you to confidently say, actually, this is noise or this is actually signal, right? I mean, that I get. Okay, and with that, I have finished this lecture, and the next lecture is much more relaxing. It contains no math, and so we just look at how to label molecules so that they can be investigated in biological and other samples using specific extrinsic fluorophores so that they become useful for microscopy. Thank you.